Okay, here we are back with big idea two, which are binomial probabilities, and you'll have some specific examples again that follow in terms of the videos, and just kind of want to talk about what a binomial distribution is. It is a discrete random variable, special type that has four special characteristics, and reason we have this is it has a lot of practical applications even by itself, let alone as a foundation for some other bigger concepts later. So first of all, these are the four characteristics, and we sometimes call these requirements for a binomial experiment or a binomial setting. One is there has to be a fixed number of trials. Two, each trial can only have one of two outcomes, or only two outcomes, excuse me. Uh, and So we consider these either a success or a failure. And a success means just essentially we observe a observation. And a failure is obviously going to be not observing that observation. So this, success can be an observation we're interested in or an outcome we're interested in. And the other one is failing to observe it. The other one is that the outcomes of each trial have to be independent of one another. And that is, if one occurs, it doesn't affect the likelihood of the other one occurring. And then lastly, the probability of observing a success must be the same for each trial. So you can see here, there's an example from your textbook, goes through and all the criteria and tells whether or not all four are satisfied. So, is this an experiment selecting 20 university students and recording their class rank? Here we can see that obviously there are 5 possible outcomes, which violates option 2. Okay, so right there. And again, all 4 of these have to hold. So if one of them doesn't hold, there's no sense in going on checking the other ones. As far as selecting 20 students from the university, and again, we would randomly be selecting those, and recording if they live on campus. So again, we would go through all 4 criteria, and all 4 do hold. We do have a fixed number of trials. That's the 20, right? Each random selection is a trial, so to speak. You have 2 outcomes, right? It's either yes or no, whether they live on campus. The outcome of each trial must be independent of one another, and that is that one selection doesn't affect the likelihood of selecting the other one. That holds here. And as far as the fourth one, the probability of selecting those students, even though if we don't know it, it's, again, let's say that, I don't know, 50%, right, or 60% or whatever live on campus. Each time we select from that population, we're going to have a 60% chance of choosing one of those students, even if we don't replace those, because again, the population you would assume at a university is large enough that those probabilities would shift so ever so slightly in terms of a practical outcome. They would not be affected. So I'll let you pause here to do the other ones. I don't want to talk through all of these, but I just wanted to explain why A was not and B was, and then I'll leave the rest for you here to go ahead and go through yourself. As far as here's an example, kind of a classic topping coins, because or tossing coins, because what we're going to be doing is, now we have these binomial experiments, we're going to find probabilities of certain outcomes. So if we get back to the heads or tails, and we see that, again, looking at the sample space, we want to know the probability of getting exactly 2 heads. This would not be using the binomial right here, okay? We would, again, look at the 8 outcomes. 3 of them include observing 2 heads, and therefore 3 out of the 8 possible would give us about a 37.5% or 0.375 probability. Now, if we look at this in terms of the binomial, and I'm kind of going through this really fast. I usually spend a little more time in this teaching a more traditional course, but this is, so to speak, abbreviated or non-traditional. So we're going to do this really quick. And if I went ahead and found the probability of getting 2, notice there are 3 different ways. And since these are independent, I can go ahead and mutually exclusive. In other words, they can't happen at the same time. I can go ahead and compute the individual probabilities, all right, which would be getting a head, head, tails. That would be 1/2, 1/2. And getting a tails is also 1/2. So that's why I highlighted these. It would be nice if we had maybe, different probabilities here, but since the probability of a success and failure are the same, I tried to highlight these in red. This would be the failure, okay? And that is just not observing a head. Well, here's the second way that can happen, right? To go heads, tails, heads. So that'd be probability getting head times probability getting a tail times probability getting a head. You can see we're applying some of the rules that we learned in week 2. And then finally, the last situation here is just, again, the failure 1/2 times the success times the success. So if we add all those probabilities up, notice we get 0.375. And you're saying, well, that's a little bit more work than maybe doing this. And you're right. But later on, when we get more trials and n grows, so to speak, the number of trials grows, this is going to get a lot more complicated. So, and this is going to be a much superior way of calculating these. Now, getting into some of the stuff that we talked about earlier, about combinations. Well, how many combinations can I choose, right, out of 3 things and observe 2 successes? All right, so this is that combination things that we worked about. Well, all this is doing is counting up the number of ways that we could observe 2 heads, and we can use that little formula there, that NCX, so to speak, in this case. So there is a general formula for binomial probabilities, and this gives us the combination right here. This is just the expanded form, and I'll show you again. We want to just always use this on the calculator. But notice all these probabilities are the same, right? 1/2 times 1/2 times 1/2. And so if we take the probability of success right here, and we put the exponent being the number of successes, and again, I know I'm going really quick here, and then 3 minus 2, which I just expressed as 1 here, and this counts up the number of ways of doing that. Notice we get our 0.375. So it's kind of nice that we have this, because this formula, you're saying, well, that's a little more complicated to use. But like I said, yeah, then going through doing this definitely is. But later on, we're going to see here very quickly that we have software or calculators to even do this part of it. Okay, so all we really have to do is observe that it is a binomial, right, where X can be the number of heads. This does satisfy all 4 conditions. We either have a success or failure. We have a fixed number of trials. Here it's 3. There's my cursor there. And these things are independent, and the probability of getting ahead on any one toss is the same. So it satisfies all the situations for a binomial. Okay. So as I move through here, you can see that if I put this in the software, okay, and this is what I'm talking about, this isn't that bad to do. All I need to do is put an N and the 0.5, and I click plot the distribution. This is in Statplet. Automatically calculates the mean and standard deviation, which we're going to get here pretty quickly, because all this is a discrete binomial or discrete random variable. And then I can use these fields down here to calculate, exactly 2, or calculate, between 2 values, including those. And this is where that gets really, really complicated with the sample spaces. It would be overwhelming to do with large N's. And even the formula is kind of bulky or difficult to use. Here's the Alex calculator, where I can kind of type it in as you see it here. And if I did hit the enter or equals button, I am going to get 0.375 on my screen here. But the Alex calculator doesn't show the calculator command and the solution. So I wanted to leave up here on the screen actually how you would type it in on the calculator. Okay, so there is a binomial calculator down here too. I believe all you have to do is click this button and put in the N and the P, and then go ahead and type in the value that you're interested in getting less than or equal to. But we'll get into that a little bit later. Okay, so but again, here is probably the easiest way. That's why I like using Staplet here. It's very user friendly as far as calculating binomial probabilities. But we'll take a look at some other examples following up. Again, here, I just wanted to show you that because it is a discrete random variable, the formulas are the same, but we can kind of use a little bit of mathematics. And I didn't do that here. I'm just illustrating the end result, but I could prove that this formula is really using the traditional formula that we talked about last video, where we take 0 times 1 or 0.125 plus 1 times 0.375, 2 times this, and so forth. Add all those up, we get 1.5. Well, as long as it's a binomial, all we have to do is take n times p, and these two numbers are always going to be the same. And again, here's the more difficult formula for the standard deviation. And we get our 0.866 here. This is the easy way to do it. Okay. And actually, the easy way to do it is just punch those numbers in here and get them directly in Staplet. So those are some shortcuts there for you. But again, here's, and all this is just punching these formulas into Staplet. Okay. All right, so I did notice that this should actually, I don't know why, that should be extended out there, okay, because the variance is whatever's underneath there. So that's a typo on my part. I'll have to go back and fix that. So, but anyway, so there you have that. That's the binomial. We'll take a look at some binomial problems here coming up, but there's the big idea.